Hello again. In this video, we're going to begin talking about the material from section 3.4, which is about the product rule and the quotient rule. And in this video, we're going to focus in on the product rule. And so let me show you what the product rule says, and then I'll do some examples to show you how it works. Okay, so basically what the product rule says is if you take the derivative of f times g, that's the same as the derivative of f times g plus f times the derivative of g. Now I want to show you a very simple example to kind of illustrate why the product rule is true. So suppose you have these two functions, f and g, and we want to find the derivative of their product. Well, one way we can do this, and this is a very simple example, okay? I'll show you a more elaborate example in a moment, but I want to illustrate something here. So if you have f of x, right, is x cubed, and then you're multiplying it by g of x, which is x to the fourth, and you want to find the derivative of that product. Well, in this case, you can actually simplify this before you find the derivative. Here you would add exponents, and this is really x to the seventh, right? So this would be the same as the derivative of x to the seventh power. And we know the answer to this using the product rule. That's just 7x to the sixth power. Okay, so we know this is a correct answer. Okay. But there are times when we're not going to be able to multiply these two functions together and simplify it before we take the derivative of it. And so we want to kind of see what would happen and try to come up with some theories about what this might be equal to. And so one possible theory of what this might be, right, intuitively you might think, okay, the derivative of f times g, it seems like it might be the derivative of f times the derivative of g. Right? I think that's a good first sort of thought about what this derivative might be. And let's check and see if this is correct. All right, what's the derivative of f? Well, that's just 3x squared. Right? And then the derivative of g would just be 4x cubed. And then when you multiply those together, you get 12x to the fifth power, which is not the same as what it should be. The actual answer we know is 7x to the sixth power. So this, our first idea that it's f prime times g prime is not correct. And in fact, it's actually equal to this, which is what the product rule says. Okay, and let's just verify that. Okay, so let's take the derivative of f times g using the product rule. Okay. Now admit, in this case, I would not use the product rule. I would just do it the way we did it up here. That would be the easiest way of doing it. But I just want to see that the product rule actually gives us the same answer. Okay, so let's follow through on the product rule. Now, one way of remembering the product rule is think of this as the first function and this one as the second one. Okay, and so it's simply the first function times the derivative of the second one, which of course is 4x cubed. And then the second function times the derivative of the first function, which is 3x squared. And now notice when you simplify this, you get 4x to the sixth, and then over here you get 3x to the sixth. And of course you can combine those because they're like terms, and you get 7x to the sixth power, which is exactly what it should be. Okay, so you should be very careful about falling into this trap of thinking that the derivative of f times g is f prime times g prime. Okay, that's not true. It's a little more elaborate than that. Okay, it's actually the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay. Okay, so hopefully I've convinced you that the product rule actually works instead of this. Okay, so let's just do a couple more examples. Okay, so here's a case where again we're trying to find the derivative of the product of these two functions, and let's use the product rule to see what we get. Okay, and let's call this the first, and the thing in the parentheses, that's the second function. Okay, all right, so according to the product rule, this is the first times the derivative of the second. Now, what I would do to find the derivative is, first you just want to, anytime you find the derivative, you always want to turn radicals into exponents first. Okay, and so let's just write that square root of v as v to the 1/2 power. Okay, and then let's find the derivative of it with respect to v. Okay, of course you can break this up and find the derivative of them individually and then add those derivatives together. And so this first derivative, so let me write it like that real quick. Right, so you can break it up like this, right? Now this first derivative, you can pull the 2 out of the derivative operator since it's a constant. And then the derivative of this would be 1/2 v to the, because you pull the 1/2 down and then you subtract 1 from the exponent. So let's see what you get here. Of course, you want a common denominator. So let's write that as 2/2. And you just get minus 1/2. Okay, so subtract 1 from 1/2 and you get minus 1/2. Okay, but then that's multiplied by this constant 2. And of course, these are going to cancel out. Okay, and then derivative of 1 is just 0 because the derivative of a constant is 0. So this is just plus 0. Okay, so this is the first. And now the derivative of the second is simply v to the minus 1/2 because these cancel out. Okay, so the first times the derivative of the second plus the second. The second happens to be this, right? And I'm going to go ahead and write the square root of v as v to the 1/2 power. Okay, plus 1. That's the second function. Okay, and then times the derivative of the first function, which of course is just 2v. Okay. And now we can just simplify it. Okay. Here you would add exponents or subtract exponents in this case. And of course you want a common denominator, so just write that as 4/2. And that leaves you with 3/2. Okay, and here you're going to distribute the 2v. Okay, so of course 2 times 2 is 4. And then you're going to add these exponents together. So 1/2 plus 1. Of course, you want that as written as 2/2, so that you have a common denominator. And so you get 3/2 when you add those together. Okay, so this should be 4, right? 2 times 2 is 4, and then v, add these exponents, v to the 3/2. Okay, and then of course, when you multiply those together, you just get 2v. Okay, and of course you can simplify this since you have like terms. So you have 1 of these and you have 4 of those, so that's a total of 5 of these. And that's your answer. Okay, so that's the derivative of this product, right, using the product rule. Now, I think in this case, if you wanted to check your answer, you could probably do that. You could do this a different way. What I would do if you want to do it a different way, just to see, is go ahead and distribute the v squared to both of these, and then find the derivative after that. And then you would not have to use the product rule in that case, right? That's an alternative way of finding this derivative. And so you could check and see if you get the same answer doing it that way. Okay, let's just do this last one here. So again, this is a product, right? It's x squared times e to the x. and we want the derivative of that product. Okay, so let's use the product rule. All right, so the first function, right, would be x squared. And then we want the derivative times the derivative of the second function. And of course, you may remember this from the last section. The derivative of e to the x with respect to x is just e to the x. Okay, so that's the first, and that's the derivative of the second function. Okay, plus the second function, which is e to the x, and then the times the derivative of the first function, which happens to be 2x, right, by the product rule. Okay, and so I think this is a perfectly legitimate way of writing the answer, but I think in the future, oftentimes what we're going to do is, now right now this is not equal to anything, but in the future, we're going to set the derivative equal to 0 quite a bit. And so just imagine if this was equal to 0, what you would do in this case is probably factor this in order to solve this equation. Now this is not equal to 0, right? This is simply an expression, and it's really not equal to a number. Okay, we're not really trying to solve for x here. But my point is oftentimes we end up factoring this. Okay, if it happens to be an equation that's equal to 0 here, then we would probably factor this. So let's go ahead and factor. And of course, the first step when you factor anything is to pull out the greatest common factor. And there's certainly things in common here. You have this e to the x that's in common, so we can pull that out. But there's also an x in common, right? You have an x here and you have an x here, so you can also pull the x out. And let's just see what we're left with. Of course, we pulled this out, right? And then we pulled one of these x's out, so that means you're left with one x. And then over here, you pulled out the x and the e to the x, so that just leaves you with the 2, so this would be x plus 2. So it's probably good practice to factor your answer, because later on, you'll certainly be doing that. In fact, when we start using the derivative to solve problems in calculus, quite often, like I said, we'll be setting the derivative equal to 0, and then we'll be solving for the x value or x values that make this happen. And so you're going to want to factor this, because then the next step would be, you would say, all right, the only way this is going to be equal to 0 is if one of these individual terms is equal to 0. And then you would just solve each of these equations to find out what x is. For instance, this would be x is equal to -2. By the way, this would be undefined. The way you would solve this is you would turn it into a logarithm. So this would be the same as the natural log of 0 is equal to x. This is called an exponential equation. If you want to turn an exponential equation into a logarithmic equation, then the logarithm has the same base as the exponential, so this is base e, which is called natural log, when you turn it into a logarithm. And then the input and the output switch because they're inverse functions of each other. So if you input an x here and you get a 0 out here, when you turn this into a logarithmic equation, you would put 0 in and get an x out. But the natural log of 0 is undefined. Okay. So anyway, this is a hypothetical. Okay, I'm just trying to give you some heads up in the future. This equation, we're not setting equal to 0 at this point, and we're not solving for x. We're simply finding the derivative of the product of these two functions, which is equal to this. But I am recommending that you practice factoring your answer, because you'll be doing that in the future when we do set this equal to 0 and then solve for x. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.